Welcome back to proof 3 of 5 on day 20, this time talking about how 0 is a right identity for addition. So the usual drill, we've got the Coq proof here, we've got the informal proof here, and I'd like to just go through line by line comparing them. So let's start the way we've done it before. So here I've stated things a little differently. I've just gone ahead and written the formal notion of the proof. Great way to go, totally reasonable thing to do. You could also have written just something like that as a title, and then expect people to know what you mean. I think the one I have highlighted right now is a slightly better way to go. I think that's a much clearer way than saying 0 is a right identity for addition, which makes sense to people who study algebra, but maybe less so to other folks. Okay. Beyond that, you'll notice there's some differences here. So we say induction and then give this sort of pattern, and then here we just say by induction on n. So this is just a Coq thing, right? That's really no, excuse me. You let me draw? This is a Coq only thing. We don't have to give any such pattern here because we can just sort of like assume the reader is following along. Now, what we do instead is that in each case, just like we did for destruct earlier, we end up sort of saying what n we're looking at. So to be concrete, in the first case, we say, oh yeah, here's our n equals 0. And then in our second case, we say, oh, here our n is equal to s of n prime. Okay, so if anything, that bit corresponds to these two cases. Okay, next up, let's compare the reasoning seen in each. You'll notice that in comments, as in many of our proofs, this is taken straight from the textbook, we end up talking about these cases again, right up over here. So let's go through the reasoning for the base case. So at this point, we're just reasoning just like we do in destruct. So the reflexivity you see in Coq is really just, okay, compute a little bit, right? That's all that's going to happen. So that's really not sort of the most complex or interesting thing going on there. The inductive case is much more interesting. There's a couple of things that are worth talking about. So one, we state our goal, and we state our IH. Let me do the IH in a different color. I'm going to do the IH in this nice pinkish red because it is that important. I'm going to underline it in galactic pen and say in rainbow pen that this is very important to state the IH. State your IH, your inductive hypothesis. It is extremely important. We will take points off if you do not do this. Stating the inductive hypothesis serves a number of functions. I think it's honestly just the decent thing to do to help the person following along. But also, in this case, it gives us, the graders, the CS54 course staff, insight into your mind. What do you believe the IH is? There's often a time where you want the IH to be some particular thing, but in fact, it turns out to be something different. So it's very important for you to say exactly what you believe you know from where you are in your induction. And of course, Windows has elected at this time to make my screen go away. I honestly could not be more frustrated with Windows right now. This is let's just leave it so that I can keep the language clean, and they'll let me leave it on YouTube. Okay. Last little bit is I want to highlight the bits of reasoning that correspond between the two. So over here, the Coq code just says simple rewrite by IHN reflexivity. So if anything, like the simple maybe corresponds to this step. And then the rewrite IHN, which maybe I'll do in that same IH color, corresponds to this step. Though really what's happening, let's do a different color, is that this goes to that by the IH. Now you don't need to say, right, like you don't need to really explicitly say that. Just set it right up here what that IH is. A reader can verify that matches. But I just want to highlight exactly the bits of reasoning going on there. And then finally, there's like some like extra reasoning. What's the color I haven't used? You look good. There's some extra reasoning here that like doesn't appear anywhere down below. Right? This doesn't really correspond to anything. And I would say really, okay, simple and reflexivity here are just tactics that are just doing the computation-y bits. And they happen to be different tactics, and they do slightly different things in Coq. But then here in like the reasoning we have on paper, you don't need to do anything else. You simply say, oh, no, you don't understand. I'm done. QED. So here we're starting to see a little bit more of a departure from, I think, just narrowly like a transliteration or just exactly closely following the Coq proof. Simple and reflexivity correspond to the broad idea of computation, but beyond that, sort of I just made some decision about, here's how I want my computation to go on paper. Whereas here, this is just like more general computation that goes a little bit differently. So it's just a different style for you to learn. I think you'll get used to it. I particularly like these chained equalities. These are a huge thumbs up to me. Love the chained equalities. I'll write that out so you can see it in the notes. Okay, that's all I have for you on this video. Sorry to get frustrated in the middle. I'll send a letter to Satya Nadella or something. And I'll talk to you soon. 2 more proofs to go.